So in section 8.4, we're going to talk about the fundamentals of probability. Probability is a measure of how likely an event will occur. When the weather forecaster said there will be a 50% chance of rain this afternoon, the probability that it will rain is 1/2. Although we cannot say with a certainty that it will rain this afternoon, we can say that if the same weather patterns were repeated over and over again, we would see that it would rain about half of the time. So we're going to first talk about theoretical probability. If we roll a fair six-sided die, we cannot be certain which number will be on top. But if we repeatedly roll the die and record the numbers, we would see that each number would be on top about once every 6 times. The set of all possible results of an experiment is called a sample space. In our die example, our experiment would be a roll of one die. So the sample space would be a set of numbers that could be on top, which would be 1, 2, 3, 4, 5, and 6. An outcome is the result of performing one experiment. In other words, if I roll the die once. So each element in the sample is a possible outcome. For each outcome, we can assign the probability that the outcome would occur. Since we're rolling a fair die, the probability of each outcome is 1/6. Thus, the probability of rolling a 5 is 1/6. We denote this as P of 5 equals 1/6. This is the probability of rolling a 5 is 1/6. For all the possible outcomes, we construct a probability model. Probability of rolling a 1 is 1/6, probability of rolling 2 is 1/6, probability of 3 is 1/6, probability of 4 is 1/6, probability of rolling a 5 is 1/6, probability of rolling a 6 is 1/6. Notice that the probability of each outcome is greater than or equal to 0, and the sum of the probabilities of all the outcomes is 1. These are two important conditions for a probability model. So here's a definition. Let S equal the set E sub 1, E sub 2, all the way through E sub n be the sample space of the probability where E sub 1, E sub 2 through E sub m are the possible outcomes of an experiment. So it'd be like 1, 2, 3, 4, 5, and 6 in our die example. And P sub E sub 1, P sub E sub 2, so on and so forth to P E sub n is the corresponding probabilities of the outcome. So like the 1/6. Then the probabilities of the outcomes must satisfy both the following. 1, the probability has to be greater than or equal to 0. And number 2, the sum of the probabilities has to be equal to 1. And note that the two conditions together also imply the probability of each outcome has to be between 0 and 1 inclusively. So let's turn to page 144 of our workbook and take a look at problem number 1. We want to determine whether the following probability models, whether the following are probability models. So two conditions: each probability has got to be greater than 0, and the sum of the probabilities has to be 1. Here, each one is greater than 0, so that's true. But if I add up the probabilities, the sum would equal 1.2. So this would be no. This is not a probability model. So check out B. Each probability is greater than 0. And if I add them up, 0.75, 0.85, 1. Sum equals 1. So this would be yes. And this third one here is not a probability model because of that negative. It cannot be negative. So let's go ahead and try another problem. A fair coin is tossed twice. Construct a probability model. So I'm going to do what's called a tree diagram. So on the first flip of the coin, you can either get a head or you can get a tail. And then from there, if I do another flip, the same thing can happen. I can get a head or a tail. So flipping a coin twice, there's four possibilities that can come out. I could have a head, I could have a head, then a tail. I could have a tail and then a head. Or I could have two tails. So I have four different possible outcomes. This is a fair coin, so each each outcome is equally likely. That means the probability of each of these outcomes is 1/4. So P of heads, getting two heads, is 1/4. P of getting a head then a tail is 1/4. Probability of a tail then a head is 1/4. And then the probability of getting two tails is 1/4. So that would be our probability model. Now let's suppose from the last example that the coin is not fair and that heads is 4 times more likely to occur than tails. If the coin is tossed twice, construct a probability model. So in terms of our probabilities, we're going to still have 4 outcomes. That hasn't changed. It's just how likely are these outcomes going to occur. That's what's changed. So let's do this. Let's go ahead and let x be the probability that a tail occurs on a single flip of a coin. So we're going to let x be the probability of getting tails. Now, getting heads is 4 times more likely, so 4x would be the probability of getting heads. So if I have a flip a coin once, I have x probability of getting tails and 4x probability of getting heads. And if I add those together, that has to sum up to 1. So that gives us 5x equals 1. So x here, if we divide both sides by 5, is 1/5. So that's the probability of getting a tails. And then probability of getting heads would be 4 times that, which would be 4/5. So now we can construct our probability model. So getting two heads be 4/5 times 4/5. 4/5 for the first flip of the coin, 4/5 for the second flip of the coin. For heads then tails, it would be 4/5 times 1/5. For tail then a heads, that would be 1/5 times 4/5. And then getting two tails would be 1/5 times 1/5. So if we go ahead and we multiply these out together, this would give us 16 over 25. This would be 4 over 25. This would be 4 over 25. And then this would be 1 over 25. So that would be our probability model. Notice if I add 16 plus 4 is 20, plus 4 is 24, plus 1 is 25. That gives me 25 over 25 and that would be equal to 1. So this is our probability model. So let's make some definitions. An event E is any subset of the sample space of an experiment. The probability of event E, if E is not the empty set, is equal to the sum of the probabilities of the outcomes in E. If we are tossing a fair coin twice, then the event of tossing one head and one tail would be the sum of the probability of getting a head, then a tail, plus the probability of getting tail and a head, or 1/4 plus 1/4 would be 1/2. When we discuss the probability of event E, we are asking what is the likelihood that event E will happen. If event E is equal to the empty set, then the probability of event E would be 0, and if E is equal to the entire sample space, then the probability of the event E would be 1. So when each outcome in a sample space has the same probability of occurring, the experiment is said to have equally likely outcomes. So theoretical probability, if an event E has N of E likely outcomes and the sample space S has NS equally likely outcomes, then the theoretical probability of event E, P of E, is the number of outcomes in E divided by the possible number of outcomes. Alright, so in English, if I'm rolling a 6-sided die, my total number of possible outcomes would be 6. That would be on the bottom. And let's say my event E is rolling an even number. Well, I have 3 even numbers I can roll. I can roll a 2, a 4, or a 6. So the number of outcomes in E would be 3, because I have 3 different even numbers. So that would be 3 over 6, which would reduce to 1/2. So let's go back to our workbook. And we want to go through and calculate the probability that a family with 3 children will have all boys or all girls. And then we're going to say, what is the probability of having 2 girls and a boy? So we're going to make the assumption that outcome of having a boy or a girl is equally likely. So first child could either be a girl or it could be a boy. Second child could be a girl or a boy. Same thing here. Third child can be a girl or a boy. So we're going to construct the sample space. So first we could have all 3 girls. We could have 2 girls and a boy. A girl, boy, girl. Girl, boy, boy. And then we could have a boy, girl, girl, boy, girl, boy, 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 girl, and then boy, boy, boy. So we have 8 possible outcomes because we have 8 different things in our sample space. So what's the probability of having all boys or all girls? Well, our sample space has 8. All girls or all boys. There's 2 ways that can happen, so that'd be 2 out of 8. And so that gives a probability of 1/4. So I'll call this part A here. And let's call this part B. What's the probability of having two girls and a boy? So I'm just going to count here. 1, 2, 3. So that's two girls and a boy. So there's 3 ways that can happen. So I'll call that part B. That'll be 3 out of 8, which we're not able to reduce that. So for numbers 5, let's suppose a fair die is rolled. We're going to let E be the event rolled an even number, and let F be the event of rolled a 5 or 6. Write the event E and F. So E is an even number. So that's 2, 4, and 6. And then F here is rolling a 5 or 6. We have here intersection. Well, the only one they have in common is 6. And so we only have one answer. There's only one number in the intersection. Now for B, remember OR here means union. So I have my sets here are the same. But now I'm taking the union. So I'm putting the sets together. Well, how many elements are in the union? 1, 2, 3, 4. Now next we want to compute P of E. So we're trying to compute the probability of E. So that's the number of ways that E can happen over the number of ways in the total of our sample space. So we're rolling 6-sided die. So our sample space here would be have 6 elements in it. So N of S would be 6. And then E, well, there's 3 ways we can get an even number. 2, 4, and 6. So that reduces to 1/2. And now let's do the probability of F. Okay, denominator doesn't change. But rolling a 5 or 6, there's only 2 ways that can happen. So that'd be 1/3. And now let's compute the probability of E intersect F. Well, we know from above here, that was 1. So that'd be 1/6. And then for F, we're now calculating the probability of the union. And we've already calculated that above. That was 4. So that'd be 4/6, which we reduce to 2/3. All right, let's look at the last one. So let's suppose 2 6-sided dice are rolled. Find the probability of the sum of numbers on the dice is 10. So that's what we did earlier when we first started working with this chapter. We had made a little table, and with that table we had on 1 through 6 here, 1 through 6 here. We found out there was 36 ways you could roll 2 dice. So that's your denominator. Now think about the way you can get 10. You could roll a 4 and then a 6. You could roll a 5 and a 5. Or you can roll a 6 and a 4. Those are the 3 ways that you can roll 2 dice to get a sum of 10. So our probability is going to be 3 over 36, and that reduces to 1/12.